Great. I am going to be presenting this paper. I've got a presentation, but I didn't put the name of the paper on the front of the presentation, so it's in there at the end, but I thought I'd bring up the paper first. There it is. I hide this. So the main job of the paper is, the main goal of the paper is to come up with a statistical method for determining causal orderings for a linear causal model. It's on the next page. Should just waited. Okay. So what is a linear non-Gaussian causal model? We assume that we have a set of variables, y, like this, and they're related in a linear equation like this. The sum is over all sets of variables y, which we can think of as having sort of this direct causal effect on yb. The coefficients are parameters of the model, and we're going to basically learn them and essentially learn which ones are 0 and which ones are not 0. And the epsilons are independent noise terms. And for this paper, they have some cases, I think, where they're non-Gaussian. Most of the cases are non-Gaussian. I think they do say some stuff about Gaussian, but I didn't look at that too much. Yeah. So it's kind of hard to look at to imagine what's going on in the other case where we're just looking at these equations. So instead, we think about our systems being like a graph, variables y1, y2, y3, y4, and they're connected in this graph if this lambda is non-zero. And we're going to assume that our graph is acyclic. So that allows us to order the vertices in such a way that I is less than j if there is no path from j to I. So 1 is less than 2, 1 is less than 3, and 1 is less than 4. But 2 and 3 could have been ordered the opposite way. It doesn't matter in this case. An ordering like this is called a causal ordering or a topological ordering. And the goal of the paper is to figure out from a set of measurements what the topological ordering is. Yeah, this last point just says that we might not be able to find the graph, but at least we can hopefully estimate a causal ordering. So the plan of the paper is basically to construct a test statistic gamma. I should actually explain what these symbols mean. So theta, little theta, just represents a causal ordering. In their paper, it's synonymous with a permutation. So it's a permutation of the vertices or an ordering of them. And we're looking for a set of these thetas such that when we are in this set, our heuristic, our test statistic is greater than some alpha. So like the 90th percentile best orderings on our set. And we want this to have a high likelihood of containing a true causal ordering. because in the last case, there were more than one. We'd like there to be at least one, a correct one in here. So for our graph with p vertices, in the last case we did 4, there are p factorial orderings to test, 1 for every permutation. So we're not going to do that. We are going to instead, the first algorithm I will present is a way of throwing out redundant tests. And to do that, we will need to test if some set of vertices U are not descendants of a given vertex V. So we want to come up with causal ordering, and so we want to be able to check to see if a set of vertices does not come after a vertex V. Regression is a way of telling if a vertex V is a descendant of some set of vertices U. So what we're going to take advantage of the fact that our graph is acyclic and sort of use a regression test like that and turn it on its head to do the other way. So this is the first algorithm, and it's a way of throwing out redundant tests. And we're going to do it in steps. Basically, we're building out our causal orderings one step at a time. So the first step is to take all of the causal orderings on one vertex sets. And then we're going to build those up to see if we can make ones on 2 sets and then on 3 sets and so on. And this gamma theta is the sort of the analog of the capital gamma from the last case, or from that we're trying to calculate, and it's the likelihood of each of these permutations or each of these orderings. So we're going to run over while we have not built up a full causal ordering of the graph. And I guess as long as there are more orderings to test, so that this is a way of checking to see if potentially your graph is cyclic, and there's some cases where you can't actually order it properly. So we are going to run over all of the permutations in this set. Maybe I should have done this with an example. And we're going to look at, instead of just the permutation theta, we're going to look at all of the unordered sets of vertices in it. So in this case, we had this causal ordering 1, and then another causal ordering P. And so we're just going to look at the unordered one. So we had 1, 2, and 2, 1. We can test both of those at the same time. That'll cut down the number of tests. And then we're going to take this V and hope to append it to the end of this list. Basically, we're going to check if V, or if the set U is a non-descendant of V. And that's exactly what this does. This is our test statistic. So we got to figure out what this test is going to be. But it's a test that takes our set of samples and a vertex V and a set U, and we're checking to see, given our samples, is U a set of non-descendants of V. And this part I didn't really understand. There was some with the way they defined capital gamma. It ended up being a beta distribution, and so they needed to check to see if this result was bigger than the alpha's quantile was at. Basically, if it's just big, if it's big enough, then we're going to add our permutation to the set. Otherwise, we're not going to. So we're going to add our permutation to the set. And after step k equals p, this will be the set of all. I don't know why there's a subdata. This will be our set of permutations or causal orderings. We're going to take this, the minimum, and so this is where we compute our likelihood of this being a good causal ordering. And we're just going to take the minimum of all of the causal orderings after each step. And yep, that's about it. I'll go back. That's the. So how do we calculate this test statistic here? That's sort of the main step that we haven't gone through yet. And it's kind of complicated. Basically, they want this. They're going to return eventually this number, and they're going to do it by calculating successively these T's, capital T's, based on regression. So they start by regressing this YV onto YU.1, and that just means you take YU.1 is just, you're going to look at all of the vector of the coordinates YU, and then another coordinate that's 1, just so that they can add like a linear or a constant term to calculate YV. And then they're going to regress YV onto that. And now we want to check to see if that is basically going to be independent of the, I guess, YV or YU, one of the two. Going to be independent of YU. Is it going to be independent of YV, I guess?
It'll be uncorrelated of YU.
Independent.
But you were, they would have tested their non. If it's independent, then you are not independent.
Okay. Yeah. This is not my specialty. I'm not.
So when you regress V on U, because of the covariance matrix,
Yeah.
then the residual is going to be uncorrelated with U.
Right.
It's like its covariance with U is 0. But it could still, because you're non-Gaussian, it could be independent.
Yeah.
So if it's also independent, which you can check by looking at the third order model, then this means that U is a non-descendant. Okay. So it could be compared.
It could also be just misspecified, right? Like the model could,
Yeah.
like the real relationships are just not.
That's probably what happens.
Yeah. And so the way they try to do this test, which they give guarantees in the paper that it works. I don't see, sort of from reading it, exactly how it for sure works, or what the intuitive reason it works is. But basically what they do is they regress YV onto YU, and they get residuals, and then an empirical distribution for those residuals. And then they sample from that empirical distribution and do this t-test again on this new. So this should go beta I. So these are the independent samples, and then they take this guy and create this Y.
And what's that capacity? That's
Yeah, so those are the, this is, those are the things that they've calculated from doing the regression. So those are the coefficients that they calculated doing the regression. Okay.
same as sampling just from Y.
I think they're checking to see if sampling from YB is the same as sampling from the. I don't know. I don't know, but it sounded to me like the reason they were doing this was because
Guess how do you choose the coefficient? And B.
those are from doing the first regression. They don't do a second regression after that.
I guess how do you choose?
You choose what?
I mean, it seems like this either would be like an independent. If you're choosing from the linear combination of the values. And you're choosing that.
Yeah.
They're like more lower.
Um. That I will get to. It's kind of complicated. But it's kind of not really that enlightening to look at it, exactly what it is. Yeah, maybe we'll come back to this if anyone has more questions. So in the paper, this T is either this T1 or T2 or both, I think, sometimes like they test both of them. And then T1 and T2 are defined like this. So there's T1 is like a linear an L1 sum of the taus, and then T2 is an L2 sum of the taus. I don't know why there's a 1 over square root of u instead of just a 1 over u. That's a good question. It's coming up next. And then tau is defined in terms of these tau j's, and it's also a quadratic sum like that. And then tau j is defined in terms of this. And the hj, this is actually sort of the end here, actually, surprisingly. So these, the etas are the ones you got from doing your regression. And then the hj's are a set of functions that you're basically using as a way to do your test for independence, I guess. So they could be linear or some more complicated. What was the exact word that they used in the paper? Escape. Escape. They used a word for the H's. They're test functions. So the test functions selected by the analyst, and they'll give guidance below on exactly how you want to choose those so that they give a high likelihood of an independent result. Yeah. Oh, I should have clicked. No, it's fine. So yeah.
You calculate this before.
Yeah.
Again, we check how many times it's bigger than the original.
Yeah. You. Yeah, basically calculate the score, check how many times it was bigger than the original. Calculate the original score, and you make new samples here, and then check to see if those new samples have a better score than the original, and the number of times they have a better score than the original, basically. And sort of the section 5 of the paper is sort of the main, is actually where they do all of their, I think, all of their new stuff, and that's basically putting a bound on this thing. To check to see if the algorithm actually gives the right bound, or gives actually converges to the thing that we expect it to. Yeah.
Like if you have a lot of samples, or you give them.
Yeah, and the exact sort of the form of their theorems are interesting. Here's theorem 1. Basically, they have all of these assumptions, and they show that it's less than some bound. But the corollaries are more interesting. So corollary 1 says, if all the conditions of theorem 1 are satisfied, and if our true f's, I should make this bigger. So the f's are the coefficients in the, here they do actually allow them to be nonlinear in some cases. I think, yeah, I think it's done with nonlinear. But later they show that, well, if you know your system actually does have linear coefficients, then you're in the situation earlier 1, non-finite basis. So it puts a better guarantee on what when your algorithm converges.
Yes.
TS. I don't remember. It's like a slight variation on T, or it's a variation on T. Maybe it's, I think the S stands for either 1 or 2. So it's either the T1 or the T2, instead of just using T.
Sorry, can you show? They're very close to each other.
Yeah.
Then why, when you do the test and you count how many times the one with the dividing symbol is bigger? No, it's bigger. Yeah, the one with the symbol is bigger than the one dividing. I guess you expect it to be 1.
I don't know.
You should.
I could also go back to there.
There's a returning that test and probably the pyramid scheme with the distribution of teams. Cells. Is it close to
Yeah, I think so.
I don't have intuition for I mean, the whole thing, like, why do they do this bootstrap? I guess what would be the simplest thing to do? You're just trying to check if they're independent. You're trying to check if their residual is independent.
Yeah.
I guess you can check that in a different way.
Right, why would you expect the bootstrap to be any different from the original? It's. That's the point of the bootstrap to be.
Yeah. I don't know much about bootstrap.
Um, but they do mention that early in the paper. At least I thought they did. No, they do allow for nonlinear. Really, their model is the more slightly more complicated. Oh, they do put the linear model in here, but they allow for the more complicated model.
The output of the, it's like a set of causal groups that are like corrected from modeling.
Yeah, exactly.
Guaranteed.
That's what they show from the, yes, that's section 5 is about that, I think. Yeah. Yeah, this is their goal is the probability that the correct causal ordering is in their set is bigger than 1 minus alpha. This is the number of samples. Yes, listed there. Um, they haven't. I did not find that. That was actually a question I did have, whether they were actually getting small sets or not.
sometimes there is more than one causal ring or graph. But if you have all of the causal rings that are consistent with your graph, that doesn't indicate that you have that. Because like if you take the path from one ring, that has one causal ring, but also like any edge you add will have the same causal ring. That causal ring has several. It's also a graded completion.
Transitive completion? Yeah, transitive closure.
Yes, there, if you have all of the causal rings compatible with the graph, then you can tell, you pick up the transit closure. Meaning that if there was a path like J, then. So, you know, yeah, I mean, I guess you also have the Markov properties. And, but then I think you can convert it.
Because the Markov gives you the skeleton too, right?
Yeah.
So you can get both there. You need both to determine the entire graph.
Yeah, one tells you like, one gives you the skeleton. One gives you. You combine them. Yeah, give some direction. Maybe that's, I mean, I don't know, like, compare.
It can sometimes give you the full graph, right?
Yeah.
You have non-Gaussian, in this case, is good, for example, we infer the direction, right?
Yeah, I think so. I need to actually check to see if where they put the non-Gaussian assumption.
I mean, that's the main.
Our first presentation, that it's not Gaussian, we can say that it being implied to the other one is very simple. But then you're.
Yeah.
However, when epsilon is not close to Gaussian, we see drastic improvements by using the residual Bruce procedure proposed below.
Yeah, so it's. Do you have any more on your side?
No, that's yeah, just a link, I guess. Bibliography.
And you can say something about your project.
I can, I guess. Basically, I've been working on the case of linear non-Gaussian as well. And the basically, I think I've come up with a way to using just relationships between moments of the variables, get another version of this kind of test. So it would just be a way to check to see if set U are non-descendant to V and just plugging it in there instead of doing the bootstrap procedure.
So you just test the rank conditions on matrix?
Yeah, a couple different matrices. Yep. That's it.
So that was not the original purpose of the project.
No. Yeah. I'm done. Right.